In this video, I introduce the generative pre-training from pixels. To fully understand the representation learning of images, a sequence transformer is trained to autoregressively predict the pixels in self-supervised learning manner without incorporating knowledge of the 2D input structure. The model consists of two stages. Namely, a pre-training stage uses autoregressive next pixel prediction or masked pixel prediction, and the fine-tuning stage uses a small classification head to measure the representation quality. Here is the image representation learning procedure. This is the input image. This is a 1D sequence. This autoregressive training procedure, and this is the BERT masking training procedure. This is the fine-tuning procedure. The model pre-processes the input images by resizing to a low resolution and reshaping into a 1D sequence, as shown here. And then chooses autoregressive next pixel prediction or masked pixel prediction. Finally, the model evaluates the representations learned by these objectives with a linear probe or fine-tuning, as shown here. Given an unlabeled dataset X consisting of high-dimensional data X, the density P is modeled autoregressively with a permutation pi of a set 1 to n, as shown here. For images, the identity permutation pi I is selected to be I, namely raster order. As shown here, this raster ordering scale, this 2D distribution, and this 1D sequence. The model is trained by minimizing the negative log likelihood of the data as shown here. Considering the BERT objective, a several sequence M is sampled such as each index X independently has a probability 0.15 appearing in M. The model is trained by minimizing the negative log likelihood of the maxed elements XM condition on the unmasked ones, X as shown here and here. In pre-training, using LAR or LBERT to train the model over the pre-training dataset. The transformer decoder with L blocks takes the input sequence X from X1 to Xn of discrete tokens and produces a D-dimensional embedding for each position. The else block produces an intermediate embedding H1L to HNL of dimension D. The following block uses this H as input to produce HL plus 1. Considering residual path and layer normalization, we have these updated equations. For autoregressive training, the upper triangular mask is applied to the n by n matrix of attention lodges, as shown here. This L, this key, and this the triangular mask here. For BERT training, no attention lodges masking is required. After applying content embeddings to the input sequence, we zero out the positions in M as shown here. This input image patches. This is the embedding module, and then we mask some of them. Then now we predict the masked tokens. To achieve higher accuracy on downstream tasks, fine-tuning the entire model, improve classification. The classification head can be attached to the layer with the best representations as shown here, which may train faster than one with the head attached at the end, as shown here. However, the classification head attached at the end is able to leverage a model depth and eventually outperforms. The linear problem can be used as a tool to measure representation quality. Fine-tuning average support NL across a sequence dimension to extract a d-dimensional vector FL of features, for example, as shown here. A projection is learned from FL to class logits to minimize cross entropy loss LCLF. The joint objective is defined as here, which includes the generative loss and the classification loss. Where this error generative can be autoregressive loss or BERT loss. For more details, please check with these references. Thank you. Bye.